5 years on from the release of Doom Eternal, we've been given another chance to sit down with id Software and talk about the tech powering their new game, Doom: The Dark Ages. In this lengthy interview, we talk about things such as ray tracing, the rise of stutter struggle and how they managed to avoid it, new features in id Tech 8, there's behind the scenes footage, and a whole lot more. So let's just get right into it.
Hello, I'm Billy Khan. I'm the Director of Engine Technology at id Software.
And what an engine it is. Yes, it is id Tech 8 time. Long in the making. This one is all about ray tracing and speed at the same time. There's a lot to get to. Doom: The Dark Ages looking phenomenal so far, but we wanted to talk to you about some of the new features, changes, and the evolution in the technology, because id Tech has been known for a while now, pretty much always, as just being extremely fast while also producing beautiful visuals. And it's that combination of the two that makes it so gosh darn excellent. So when you get to id Tech 7 with Doom Eternal, it's still a great looking game. And you even added ray tracing to it in a patch, which is awesome. So ray traced reflections made it in. So when you're saying, all right, we're going to next generation, we're moving to the next iteration of id Tech, you know, every studio has a different approach to this. How did you guys start when moving to id Tech 8? What were the goals that you had from the beginning? And talk a little bit about that process, if you don't mind.
First of all, hello, John. It's an honor to be here, and I'm really looking forward to talking to you and everyone about Doom: Dark Ages and id Tech 8. I would say it's a long-standing process, and it's not something like you don't finish a game and immediately say oh, what are we going to do next? Some of these things that you're seeing now are things that we thought about for many, many years, even if up to 10 years for myself, where we make incremental changes of some of these iterations of the engine, and we plan for them where we put modular components into the engine that we can expound upon as time goes by. So some of the features you're seeing now in id Tech 8 started off at id Tech 6, where we started a process. Okay, when we get to id Tech 8, we need to be able to handle these type of workloads, these type of graphical fidelity, these type of size of maps, these type of complexity in our pixels and our lighting, etc. And for each iteration, we were slowly progressing to where we now are with id Tech 8. So some of these features are features that we've been long working on, and you saw that progression over time with all of our titles. And some of them are obviously, whenever we make an engine, it's always purpose-built for the game that we're working on. It is very important to us that whatever we provide has a direct impact for the player, and that the immersion that the player feels is related to the content we are able to create, their input, what they provide when they're playing the game, and making sure that the tech can give the feedback and provide the means to display all that stuff in a really fast frame rate to give the best player experience that we can think of. So it's a combination of both. It's a thinking about what we need for the product and making sure that all those needs are met. Having forward plans, like a roadmap of what are the technology advancements that we'll see over time. And then, of course, some of ad hoc stuff. As you develop, you find out things that work and don't work, and those are usually the gems that you get when you work on things and collaborate with your teams. Because it's all, I think, the magic here is the collaboration between the departments. It's the symbiotic relationship between the artists and the designers and the engineers and the producers, all working together towards a common goal. Oftentimes, it's wrongly attributed to just one department or few individuals, but that's not the case. It's a team effort, and it's that team communicating and working together that makes the magic shine. So, and our job on the engine side is to provide all the capabilities for the team to do all that work.
Oh, and I guess it's that teamwork that sort of ties into one little issue as an aside. Something that we've talked about a lot over the past few years is stutter struggle.
Yes.
A lot of games have stuttering on the PC, especially. Traversal stutter, shader compilation stutter, just stutter. And we've been pushing back against this as much as possible. It's a very, very complicated issue. It varies a lot per engines, but it's not a problem that we've encountered in any id Software games, including my time with Doom: The Dark Ages and the prior id Tech games. Somehow you're able to do these massive games with extremely short loading times, no obvious shader compilation pre-step, and yet there's no stuttering. How the heck are you guys achieving this?
That's a very good question. I think it's a multifaceted question because there are a lot of moving parts
Right.
on how we get there. One of which are, first of all, is our design and philosophy when it comes to writing code, and how we approach our engine when it comes to shaders. One of the main things that we do is we try to make sure that we have a minimal set of shaders that can do the most amount of work, that has multiple facets to it. It's much easier for an artist to understand a complex shader and all the intricacies how that works, rather than having thousands of shaders that you have to maintain. Second of all, it allows you to fine-tune that shader, and if you make a change there that has a meaningful performance impact, a vast majority of content is affected by that. So if you make a mistake, it makes many things slower, but if you make an improvement, many things become way faster. It also becomes like having pieces of the engine or shaders or materials even where the artist can really learn their craft. Like they really understand how it works, they find the nuances, they understand the places where they can push and pull and then provide feedback, and then we can iterate on those concepts and make them better. If you have thousands of shaders, it's very difficult for that complexity to get the same amount of detail and focus to make them as polished as you can. You might have some that work really well, you might have some that look really great, some are somewhere in the middle, and then you have these things of deciding when those get executed. And the GPU actually has a big problem constantly having the context switch. So that has a
Right.
problem on compilation times, has a problem at runtime. So that's one of the things we do. There are also things such as really being particular about making sure that we take latency into account. We don't want any bubbles between our passes, and variance in where our passes of workloads or jobs have big variances in between frames. For example, if I have a certain job or workload I need to do, we kind of want to be doing that same type of work every frame that's predictable, and not have it like one frame it takes some 100 milliseconds, sometimes it takes 5 milliseconds, because that causes those frame bubbles and that stuttering to occur, because you might have really fast frames or really slow frames, and then the GPU gets out of sync with the game, and that causes issues. It's very important to keep your frame time in check and as homogeneous in the same type of variance as you can, or minimal variance as you can. And that takes a lot of effort from all departments to make that happen. On all fronts, not only on coding, on art side, on making sure that the assets and how they're being created, how many things are in a certain sector, for example, of a portion of a level, how fast does the weapon fire, when do we spawn an AI, all those things are done meticulously and nuanced to get this effect.
Another major feature, though, that I want to get into as a completely separate thing, so we only have a limited amount of time here, but one of the big engine features here, of course, is this focus on ray tracing. And this time it seems so with Doom Eternal, you went for sort of like ray trace reflections across the board. And it seems we saw this first in Indiana Jones, which Machine Games, I guess, works with you guys closely to develop their own sort of take on id Tech, which they called, what was the name of that?
It's Motor.
I'm forgetting the Motor. That's
Yes.
right. It's Motor. But of course, Doom: The Dark Ages also has ray traced global illumination, in addition to ray traced reflections. And I'm not sure. Basically, I would like to hear your take on how you implemented this and how you were able to accomplish everything while still delivering 60 FPS across the board. So, obviously consoles as well, down to the Series S, I suppose.
Yes.
Needs to be 60 FPS.
Correct.
So, first, let me hear about the ray tracing in general and how you approached it, and then secondly, we can talk a little bit about the console side of things.
I mean, ever since I started programming and graphics, I've been wanting to do real-time ray tracing. So it was a dream of ours, and particularly mine, to make sure that we could do these types of things now in real time. But more importantly, we saw that the hardware was progressing. We made those changes in the Tech 7, and we made some great strides in an Eternal when we provided those features to the player base. And we saw that, like, okay, it's a precipice of being really great. And we knew that we were wanting to make a much larger title, especially with the theme that we had with the Dark Ages. We were going back in time to talk about the story of the Slayer. And then when you go back to the Dark Ages, you can envision that those battles that he had to fight were grandiose, and there were many more enemies on screen. And how did he become the Slayer? So that story required a much larger level of detail, much larger worlds, and to make these gigantic levels. And just to point out how big they are, on average, our sizes of the maps are about 5 times larger than what we had in Eternal. And then if you take into account some of the maps where you run around in the Atlan, those are like up to 10 times larger. And the funny thing is, as you're running around in the Atlan, for example, because the Atlan is so large compared to all the little like AI or even the Slayer, comparatively speaking, the map being so large, it doesn't feel that big because you're in this gigantic map traveling really quickly through this level. But in reality, you're traversing like about kilometers per second really quickly, so the maps have to be really large. So we knew that was a big thing that we needed to do. And what that means is you have to create a lot of content, and you have to be able to iterate on that content very quickly. And what if you notice from ITech 6 to 7 to 8, one of the big focus things, and now moving forward, was the focus on iteration, so we can really, really make sure we can create a lot of content really quickly, iterate on it, and because the more you iterate on content, the better the end result is for the game. More polished it becomes, the better it looks, the more gameplay variances we can make, etc. And ray tracing allowed us to do what we call WYSIWYG, which is basically what you see is what you get. In prior iterations of ITech, the artists or the lighters or the people working on the content, the designers, they would place things in the maps in its studio, and the lighters would place lights, but then you would see a representation or approximation what the game would look like. And you would have to then say, well, I kind of think this will look a certain way, and you had the mind's eye about what the vision might be, but then you had to go through this process of baking of either light maps or virtual textures. And then even though we had processes to make that appear within minutes, or sometimes these things would take hours, like certain maps or the final bake would take hours upon hours. And what we have now with ray tracing is that it's all gone. An artist places a light, and they will see exactly in its studio what it's going to look like in the game on a console, because we're able to show exactly what that will look like. Now, you can imagine what kind of speed improvement that's. That's almost many times 10 to, if not 100-fold improvement in iteration time on various fronts. A lighter can move. A light in the middle of a meeting. Hugo may say something, hey, I want this to be darker. I want to add more ambience here. I want this to be more moody. A lighter can, while we're in this meeting, go in, bring up its studio, tweak the thing, and immediately iterate on that. And if you can imagine what kind of power that gives to the development from a creative side, and the ability to craft a world that is so immersive and fun to play in, it was a natural progression. Now, for the player, on the end of the things, you also see the improvements there, for example, for our cinematics. The visual fidelity we have in our cinematics has gone up much, much higher, and that's attributed not only to ray tracing and the atmospherics we worked on, but the ability to have a pipeline now that allows the artists and the animators and the cinematic team to really work on their craft very diligently and very quickly, and that allows us to polish those things. And if you noticed, those cutscenes are running in real time. Every single time you play the game, you're running them in real time, so we can do cool things like replace the content. We could even have, if you wanted to, we could insert things at runtime. We could have, like, if you might have a different skin on, it would show up properly, etc. And so ray tracing was just a natural way of not only improving the title to make it look really great, but also allow us to make a better game.
Oh yeah, of course. That is awesome. I mean, I've never used id Studio myself, of course, but I have definitely built things in Unreal Engine 5, which has its own system, which is Lumen, of course. And just being able to immediately light it in the editor itself and see how it looks and get those results when you spit it out, it's a game changer. So it's cool to hear that it basically allowed you and the team to much more agilely move through development and like build these huge maps that I'd imagine if you're trying to pre-calculate everything all the time to see how it looks would have taken a prohibitively long amount of time given the scale. So
Without this feature, I would say we would have had to elongate the development time by a magnitude of years, because the amount of ability to create this, I mean, we wouldn't have been able to create the same type of content. You really can go now into the nitty-gritty and nuanced things that you may miss because you can do it so quickly. But not only that, it's from a feature standpoint, from a player's perspective, we also have this concept of providing more feedback to the player when you play the game. We really wanted to make sure that the Slayer felt really powerful, even more so than even in Eternal or in 2016. And one of the things that we added in Doom the Dark Ages was the concept of, like, you know, more immersive gore and more immersive world destruction, so the weapons felt really powerful. And if you have a baked lighting solution, then some of those things can feel out of place, especially when you have really, really large objects. When you're running on with a mech and you're smashing buildings and pieces fly off, you can't have those things be baked. And if they're not baked, then the ambient lighting will be completely off. With ray tracing, all that stuff looks homogeneous and it feels more real. It feels more impactful, and it really makes you feel like you're in the mech or you're fighting as the Slayer, because things look like how they're supposed to look.
Yeah, actually, that's quite interesting. As that's something I pointed out in my preview video for Doom the Dark Ages, was when you destroy those buildings, which is something I want to talk about shortly. Like, they actually get the proper ambient shadowing, right? Because it's like lit under the building, and then as it falls, you actually see the proper contact shadows all just form naturally, which wouldn't have happened if this was all pre-baked.
Yes.
So I guess the question then is, this is not just a PC game. There's also the console versions. Do you have full ray tracing across the board on all the platforms, including Series S? And, well, first of all, do you?
So ray tracing, every single platform we ship on is ray tracing required. And luckily all the platforms have ray tracing, which is great. Now, there are obviously differences in between the platforms because of the different capabilities. But we were able to pull off and make sure that that the game feels as close as we can make it identical between all the platforms. There's some variances in resolution, but the frame rate is the same. We wanted to make sure that if you're playing on one device versus another device, you still get that great 60 hertz feeling, if not better. So because that's really important to the feel of the title and how to make the Slayer feel powerful and the player feel powerful as playing as the Slayer. When it comes to ray tracing, everything has ray tracing. There's some nuances of when SSR might kick in for some of the reflections.
Sure.
And there's some compromises we have to make in some of the minor details we have on some of the composite materials we have. But for the most part, everything renders the same, goes through the same process. The render behaves in the same fashion. We didn't write like, the console version, the PC version. It's the ITEC 8 is running on the device, and we have some knobs to push and pull to make that work.
And so that actually highlights sort of like one of the cool things here is because Doom Eternal's ray tracing update did not ship on Series S, right? It was only on PlayStation 5 and Xbox Series X. But now here we are, years later, you've got Doom the Dark Ages, which is a much larger game, more detailed game, and you actually did manage to get it working across every platform. So,
yeah,
I mean, I think that's pretty awesome.
Well, thank you. Yeah, the team worked really hard on it, and kudos to the team. Kudos to Tiago, Bogdan, Jean, Oliver, everybody working, Philip, Donamic. I can keep going, rattling off names, Ishan, Alan, etc. Seth. I mean, everybody did their part to make that work, and it's on the content side, the content creators really made that work out great, because they gave us feedback where they wanted the features to work and what features they needed, and optimizing their workflows to accommodate this, but also making the content in very precise ways to make sure that we could render these things very quickly.
The next thing I want to talk about, so something I noticed while playing the demo of build, is that aside from some foliage here and there, the game does a fantastic job of sort of masking any sort of level of detail transitions, right? So, large open map with a huge view distance, but when you're looking at rocks and such, outside of, like I said, a little foliage here and there, like a texture here and there, it's by and large very, very solid. So it reminded me of what we've been seeing with more modernized virtual geometry systems, but I'm not convinced necessarily that that's what it actually is.
Yeah.
And I'm curious if you can shine a light on what you guys are actually doing here to achieve this.
Well, it is not a new geometry system as you're describing, even though we're working on something like that. But what we're doing here is we first of all, we expanded our number of LODs that we have. In the vegetation front, we even do some things like, for some LODs, as we transition for the vegetation, we do a morphing between the two LODs, where it slowly transitions to that, and there's like this interpolation that's happening for some of the LODs. It's not happening on everything, but on some, and that's particularly vegetation. Some of the grass foliage where we have is all dynamic GPU grass, right? So that can scale through heuristics with the GPU based on distance, and we can actually, since it's all GPU generated, the vegetation actually tessellates a certain amount. So on those fronts, there is some dynamic stuff going on. There are not many places where that's being utilized just because the game didn't need it. But there are systems in place. We also have a new system that Oliver implemented called our Auto Vista Log generation. And if you notice when you play certain games, like you're running through a game and you see a gigantic castle and you're like, ooh, at some point I'm going to reach this castle. And back in the day, the way these things were done and even in our titles, were like, oh, I'm going to make a Vista model out of that. And it's like a model that you see when you're in this location. And as I get closer, at some point I have to now load up the real asset, right? And that process was usually either done through a skybox or some custom geometry. And, you had to like run through certain pathways so you can see the pop. And what we have now is we have our designers and our content creators, our level designers, are able to just build those spaces out, to populate them with the AI and all the content, with all the little kid pieces that they have. And our Auto Vista Log code takes those play spaces, and the designer gets to pick the area that they want to create this for, like that they want to make a Vista lot for, and it automatically creates these LODs out of the content that's there without someone having to handcraft that. And then because we do that automatically, we can then create LODs that allow us to fade that in a meaningful way that is almost imperceptible to the human eye. So as you're running towards the castle, it may transition from an auto-generated LOD version to something that actually formulates with all the individual pieces. And obviously there's some trickery going on with placing some things that as you're running through the forest towards the castle, you might see, so that distracts you where there might be some anomalies. But all of that is magic or illusion that is done through content and some special code that we fine-tune. We have this concept of contribution culling, where we have all these different features that we can dial in based on distance. And the contribution culling allows us to then, on the data front, really tune in per platform how these things fade in and out. So there might be some features on the shading side that slowly fade out, which gives us some performance. And as those things fade out, then it's not always like I'm popping from LOD to another LOD. It can be first fading out some features that like smaller details, and then it might go to a simpler shader, and then at some point while that's happening, we might go to a transition to an LOD, etc. There's all these different systems working together to give you that effect.
Very cool. That's interesting, and it is actually very effective. So
yeah,
I think the results do speak for themselves. So interesting.
Yeah, we have this concept of better pixels rather than more geometry necessarily. And what that means is we rather than just always increasing resolution, we want better pixels, right? Does the pixel convey what you want it to show? And if the pixel's lit properly and it shows the right data, then it doesn't really matter how many polygons you have. It really matters what you end look at. And so this concept of having better pixels, we think about it from those aspects of the contribution culling, of how we transition from LODs to another, how we do that through content, what the pixel density is or the texel density is on screen based on the size of the object, and keeping that as uniform as possible through the scene. Though all those things play a big role on making that look as detailed as we can make it, depending on what you're looking at.
Cool. Another thing though that caught my eye, and I mentioned earlier, actually, is the physics system.
Yeah.
So the way I look back at this is when I played the demo, I really realized what was going on. I was like, wait a minute. It reminds me of the shacks that used to be in the original Crysis, where you have all these little structures dotting the landscape, especially in the open world areas, right? Where they're all comprised of, like, you got poles, you've got like the ceiling bits. It's actually like constructed like segments. And what's cool is that they can kind of break apart and splinter, and like it actually reacts to the action on screen. So obviously, ray tracing makes it possible to have that in the scene lit, because Doom Eternal and 2016 and all that, obviously Rage especially, if you go back, have nothing like that, right? There really isn't anything in sort of these physical interactions. So one, I'm curious about how you actually approach this problem of getting this into the game, what sort of performance cost you're looking at there, and I'm also interested just to know, like, was this actually like a big part of the design where you actually were thinking like, yeah, we want to make sure we have these cool physics interactions, or was it just sort of like a chance thing where somebody's like, hey, I made this cool thing, let's stick that in the game?
No, all the things that we do are always planned out, and,
of course,
and they are in a way that they add meaning to the player, right? We wanted the Slayer, as you're playing as a Slayer, you want it to be feel as powerful as possible. And if your gigantic projectiles that you're firing from your weapons don't have an impact in the world, that kind of diminishes the impact or the feel you get. So in this game, since we wanted to make sure that not only could we have lots of characters on screen, we wanted to have a dynamic gore system, and that also meant world destruction to some degree. Not to the extent where you can just smash the entire level, but meaningful gore destruction that makes an impact for, like you say, those crates and the structures that you have, or even when the AI run through the level and they might be smashing through those barracks, and then makes them feel powerful. And then if you then take them out, you feel powerful because you just saw them run through half a building, but you took them out with a punch, right? And all that plays into the power fantasy of being this really strong, like, stand and fight mode that you're in Doom: The Dark Ages. So we obviously using Havoc, and we worked very closely with the team at Havoc to make sure that we built tooling that allowed us to create that content very quickly. We Peter and Stefan worked very diligently on making sure that was as optimized as we could have, so we have thousands of many objects working together, and that those collisions, those intercollisions of those rigid bodies, they were solid, and then that they felt weighty, and they felt like they had mass to them, and that you didn't have those things where things interpenetrate, or you have sometimes things hit each other and then they go spin out of control because the simulation wasn't stable. That took quite a bit of effort, especially when you have such a dynamic game like as the Dark Ages, where you have all these things colliding together, and what the player does, you have no control over. So the impulses that we receive can come from any angle. So we worked very diligently on making those things as stable as we could, and that took a lot of effort from Peter and Stefan to make sure that we built tooling and optimized our physics code to make that as stable as it can and as fast as possible. To make that also work, we had to do a lot of work on the engine side, on the GPU side as well, because the more stuff we can push off into the GPU, the more CPU time we can dedicate to the simulation. Sometimes you have trade-offs to make where, like, you do a lot of work on the CPU and then you cannot dedicate quite a bit of the jobs or the cycles that you want to spend on the simulation for the physics. And because we optimized our rendering so much that everything is now done on the GPU, the entire scene graph is done there, all of our culling, everything. With CPU now has the luxury of being able to just focus on physics, sound, and gameplay. And because we have a highly optimized job system and scheduling system that takes all these varying components and arranges them like a jigsaw puzzle to execute as fast as possible, we were able to make sure that the simulation was always stable running, get enough dedication of time, and it could also run in a higher frequency so the simulation would be more stable, you know? Especially when you have really fast moving projectiles. Oftentimes that movement is like taking a bounding box and projecting into space, and as it travels between frames, you have to make sure that you can it might be that you're traveling through the world in such a fast pace, but even between 1 or 2 frames, that you have to simulate and make sure the simulation can and backtrack all those steps that the object in the real world would have gone through. So that means you have to simulate the physics in such a way that actually takes that movement into account.
Huh. Very interesting.
Yeah.
And I guess it also kind of explains how I noticed once a building or structure, things have been knocked down, there's debris on the ground, the simulation seems to remain active.
Yeah.
So you can walk through, you can shoot it, and it just continues to update. Whereas a lot of times, once the physical destruction has occurred, it's sort of deactivated to save on time. And that's not the case here. So very, very cool.
Yeah, just to ping on that, we added some more nuanced code there. Like usually in the past, what we've done was like you would activate something, it would explode, it would come to rest, and then we would turn it off. What we did here is we took that notion and we expanded about it and said like, well, actually, we can put it to rest until there's a new impulse coming out. And if we notice there's an impulse coming up, then we can reactivate it and let it do things and only allow it to simulate when we need it to. So there are some pieces that go to rest always. There are some pieces that can be reactivated that are meaningful to the player experience. And some things obviously don't ever get bounced around because they have too much mass or we don't want them to. And that interplay and connectivity gives it that extra feeling of like everything works, right? Because if you build the system in such a way where you can tell like, oh, that looks heavy, it's very unlikely I can move that. It makes sense that it comes to rest and then stops, right? Whereas if you have a small piece, oh, that's like a piece of rubble that came off the statue, I should be able to shoot that. Then in those cases, we might allow it to reactivate and then fly through the world. That doesn't happen for everything, just some of those things.
I even noticed little details like in the second level when you're walking around these like precarious railings.
Yeah.
Just the weight of the Slayer's like character model. You just walk into it and like snaps off and falls away. There's a ton of stuff like that. We're just walking through it is enough to break it apart. It feels great. So,
yeah, we wanted the Slayer to feel like a tank, like he's like an Abrams tank going through the world, like he's heavy and weighted and grounded, and that you really just have to stand and fight, right? To take them on one-on-one. So that's done through the physics, that's done through the animation, that's done through the sound, it's done through the feedback of the weapons, and all those things coming together and really being able to polish those makes that experience that weighty feeling. Especially for the Atlan too, because when you're in the mech, Atlan mech, you have to feel powerful, right? So
yeah, you need his physics and breaking apart the facades and the buildings and such, and I like that stuff.
Right.
And of course, you also need crowds, which is another thing. So ever since Doom, Quake, whatever, transitioned to polygons, the big sacrifice has been numbers, right? Enemy counts have had to go down. And I think it was at its lowest in something like Doom 3, which was a much slower paced game, of course, but with all that advanced lighting, you can only have X number of enemies on screen at once, right? Dark Age is the first one since the 2D sprite-based Doom games that feels like it actually has like those large numbers of enemies in the battlefield. So I'd like you to talk a little bit about how that was accomplished and how you're able to do it at speed.
Obviously, the physics had a big role in that. We needed to make sure that the ragdolls and all those things were highly optimized. Our animation system got a major overhaul and make sure that ran much faster. Pushing everything from the CPU and onto the GPU to allow the gameplay, the physics, and the sound to just be able to run almost entirely just on the CPU, and doing all the rendering on the GPU allowed us to free up more cycles so we can do more characters, right? So there can be more game code executing. There can be more AIs running around. They can do more thought that they're thinking. Each AI's thought process and how they behave through the world and react to the world and how they choose paths, for example. All that stuff has more time. But the team also really spend a lot of time optimizing. One of the key things when it comes to optimizing on the CPU is really just access of how we access memory. And we spend a lot of time on the game side of things. The system programmers on the gameplay side, Jacob and his team really worked on a new way of taking all the entities that we had in the world and made sure that the memory that they consume was all aligned in a very particular way. So when we have to fetch data for a particular object, that most, if not all of that data is actually meaningful data that you want to use for the current time of the calculation. And in the past, one of the major slowdowns you have on the CPU time is when you have, imagine you have all these entities and they have a bunch of data with them. And now every time you want to go do something with an AI or an object in the world, you have to fetch all this data. And whenever you fetch the data from that and you have to go to 10 different places, that referencing from different spots in memory, it can be very, very slow. That's how you get cache misses. That's why, if you look on modern CPUs, they have all these different cache levels. You have your L1, L2, L3, etc., and they have all these different sizes. The way I attribute it is, let's say you're cooking a meal, and you're making your favorite dish, and you have some ingredients that you need ingredients to cook that dish. And imagine whenever you're trying to cook, some ingredients you have really next to the stove, like your salt and pepper. Some ingredients you have in your fridge, that need to be refrigerated, and those would be attributed to what you have in your cache potentially. It's slightly slower than being right next to you, but they're fairly close where you can just go into the fridge and grab them out. And some things are at the store or in your pantry. And whenever you imagine, in the olden days, back in the day, or before, in previous versions of our tech, or even on other, what games usually do is, some fetches are like the same cost as if you had to, I need to now get onions, and you had to drive to your store, purchase the onion, drive back, then you have to chop it, and then you'll be able to use it. Really, what you would want to have is make sure that you have all the ingredients to make your dish right then and there. Maybe the analogy is a bit silly, but it kind of tells you that memory access can be quite slow, and the analogy of having to go to the store to pick up each ingredient separately is really shines a light of how slow some of these things are. So Jacob and the team worked on a factory system and alignment things where the entities are now component based in a certain way, where the memory that they need to some of that work, like the AI's workloads, are aligned in such a way in memory that they're right next to each other. Meaning that if I need to now do a path, or I need to do some calculation, I can fetch that information, and I can prefetch that information in such a way when I go to the next 2 or 3 entities, they already, as the cache is being filled, as I get to that memory is there, and the memory that's there is actually meaningful, rather than having to jump around there. And you can get up to a 10x improvement in speed just by doing that. You can have the exact same code, but if you fix your memory fetches, you can get a 10x improvement in code. And I would venture to guess that for our titles, and every game code has this problem, right? There's a balance between what code do I keep resident, what data do I keep resident nearby, and what data I do need to put a little bit further away, and I want to access that infrequently. And obviously, because bandwidth is limited on memory fetches, and you have a limited amount of memory, you have to be very clever about what you choose to pick in there, and that takes heuristics, that takes timing, and really understanding the behaviors that the code that you're trying to execute is doing. So the AI team, Jacob's team on the systems gameplay time, did a wonderful job on working on that, on top of all the wonderful work that Oliver did on the scheduler, and making sure that all those different jobs that execute are done in the most efficient way without having any type of bubbles and removing any kind of sync issues. And that's just the progression of the work we've done from ITech 6 to 7 to 8. It's just a natural progression improving that. In particular, when it comes to Oliver's work, Oliver worked really hard on making sure that heterogeneous CPUs were scheduling their work properly, because you now have this concept of power cores and efficiency cores, whereas some CPUs have homogeneous cores where all the cores and threads are the same and they behave in the same rate. with heterogeneous cores, you have to now balance the work between efficiency and power cores, which means that some work has to go on some of the power cores that's more that are maybe more streamlined, and some things can go in efficiency cores, and doing that scheduling can get quite tricky.
Man, so see, folks, I think that's a lot of the id Tech magic secret right there. This kind of optimization, really paying attention to the nitty gritty, understanding where things are in memory and planning that out. That's really cool stuff. Very, very cool. I love that. And I wonder, maybe you could talk also how this applies to loading times, because I was astounded to find that the loading times on my system and the test system when I did the demo were like faster than Doom Eternal.
Oh yes,
they're so fast that even if I had like a major load, like I told you beforehand, I was encoding a 4K video on my PC, and I still loaded up Doom: The Dark Ages, and it was still playing at a high frame rate, and the loading time was still faster than Doom Eternal. And Doom Eternal is really fast, by the way. So like, it's basically so fast that I feel like a loading screen is almost not even necessary at this point. It's just like a dip to black, and it's just like you're in the game. So, like, what the heck are you guys doing?
Yeah, that's intentional. I personally dislike loading times. Like, I don't like waiting on things.
Me neither.
Maybe I'm a little obsessed with efficiency, and I think the team is also, we love efficiency, and we love speed. And I don't like anything that wastes time, so loading to me is like a waste of time. I want people to be able to get in. We all have limited amount of time to play games. I want to maximize that time so people can get in, play the game, and get as much enjoyment as they can. So loading time, getting that fixed was a big improvement, and Oliver and the team worked really hard on that. There are many things that we did. We needed those larger maps, right? And because the content is so much and the world need to be much more dense, there's only certain amount of memory that you can have and load things in. So what we did is we introduced this concept of sector streaming. And just think of taking these gigantic worlds and compartmentalize them into cells or sectors or spatial kind of grids type of layouts that the designers decide how they look. And that not only allows us to make sure to be focused on the things that immediately need to be loaded in first. Traditionally, in the past, we had to load in the entire level, and that takes a lot of time. But what we can do now is all that content we used to load for the entire level, we can now cram into pretty much one or two sectors. So that means you can have much higher fidelity of data in much more dense worlds. But it also means that we can partition the workloads in such a way that we can predict where you are in the level and then load things up as you're running through the level and stream them in before you even get there. It also means that when you first start the level, you don't need to load everything up. So we only need to load the things up that are immediately there. That speeds up things. The combination of aligning the data on the gameplay side and how like I just talked about how the runtime, that also has an effect of how fast you load, because you only load the things that you really need. There's a lot of work that was done on the compression side when it comes to our images and our texture streaming, for example. We have everything is being streamed now, whereas in the prior titles, some of the pieces that we needed a lot were not streamed. We're streaming now animations, all the geometries now through a World Geometry Manager that has been got a major overhaul on how we stream those things in. We have more LODs, so we can do some trickery there and what gets loaded in, even though on the geometry side, we generally load all the LODs in up front. And the prefetching is a big thing. The Vista Log generation of the tooling had a big impact on that because, we only have to load in pieces that are required as well. So there are content changes. There are many improvements on how we load textures in, like for example, on Xbox, we use direct storage. And we have we also formulated how our resource system has that stuff partitioned. Our stream database is really optimized to make sure that the data that we need at the time is loaded in a very particular way. And that all leads to like sub-second loads many times. And for the most part, these pause screens, people wouldn't realize. It could be that people are like, oh, when is it done? And we had to put a button in there and let the player know, actually, you can play, because they're like, it was so fast that they can't even read the text that we have or the information that sometimes we will show between levels, right? And oftentimes people don't realize that it's already ready to play, right? They're still reading the text,
Yeah,
and you
exactly.
can just like immediately play. So that's a great problem to have, and things are so fast.
It's so fast that I'm wondering. It's like you guys should consider putting an option in the menu, say, please disable loading screens, because you don't need them. It's that fast. 'Cause-
Yeah, yeah, we could do
Right?
that. Maybe we'll do that next time. Maybe we do one of the things that we might try out for Attack 9. And again, this is just hypothetical here.
Right,
Is
right.
just have it so you never ever see a loading screen, and you just play the game as one long stream. And you basically start the game
Interesting.
out, and you're in the game, and then you never there's
Yeah,
no
yeah,
loading
yeah.
screen, there's no level loads. But there's a on the gameplay side, there's a finality, there's a concept of like rest, that level loads still are nostalgic to us, right? There's a sense of accomplishment of like, I finished this level and I get to, do the stuff. So, there are some gameplay pieces where we might not want to do that, even though we can or could do that. So we have to see. I have to keep you posted on that.
That's cool. That actually kind of brings me to one thing I wanted to mention. It's like, could you talk about maybe something that you're most proud of for ITech 8, and then something that you perhaps would want to do in the future with ITech 9 going forward? Something you didn't get to do this time that you maybe have your eye on for the future, where you're like, that would be pretty cool. You can have a moment.
You want the secrets. I think one of the most rewarding things for any graphics programmer or programmer in general is when you create technology and empowers really creative talent to be able to shine and do the best work. And so the tools team, Darren and the team did a fantastic job making sure that our tools were always extremely stable. No matter what crazy code we threw in, the code base was the most stable we've ever had. We had very little downtime when it comes to, and the funny thing is, making sure the stability is there allows us to create stuff in there, and within 4 or 5 minutes, a designer or a programmer or an artist can have that new code and finally do their work. So that iteration time and making sure that that's fast, and providing the tooling for us to, and the rendering capabilities and all the new lighting techniques, etc., to empower us to do the cinematics, because I think the cinematics tell a really great story, and having that capabilities of making those really look shine and do them all in real time, and allow the creative team to really stretch their legs to do this awesome game, is probably the most proud. It's really seeing the results, because in the end we're all gamers, and we want to make the best game we can, and then seeing that enjoyment and the reactions that people have when they get to play the game, that's probably the most fun. So that this period right now we're entering, where you get to watch the Twitch streams and the reaction videos that they all post, and the enjoyment it gives, that's probably the most satisfying part for a developer to see when the game comes out. But during development, also see the joy that you give to your co-workers and peers to be able to do their best work. I think that's the most rewarding part, for at least from my standpoint.
That's super cool. Okay. Then I guess anything about the future is probably top secret still. But is there anything where you're like, that you maybe wanted to do or you didn't get to do this time, where you're like, man, I would like to be able to do this?
Obviously, I want to push ray tracing further. I want to do,
Right.
ideally, I would love to do just full path traced everything.
Oh, the whole time, yeah.
Yeah, all the time for everything. I want to see how far we can go with graphics when it comes to cinematics. I would love to obviously just have the ability to just do continuous playing of the game and never have any downtime. I would love to see be able to make the game so scalable that it can run on any device pretty much as we can. So just empower us to do many more, allow more players to enjoy our game. I think expanding the player base and Doom just needs to play on every device it can, or as many devices as it can. You want to keep that tradition going, so keep working on that and making sure more and more devices can play it. We're in an inflection point now where all the platforms we're shipping on had ray tracing, so we decided that was a good point to make this call. So really going in on ray tracing and taking it to the next level is probably what's next for us. I would also say, being able to just create more immersive, better player feedback at higher frame rates, is always a goal. I do think we've come to the point where we're good enough when it comes to resolution. I think, I don't think 8K is really the future, even though then you have these gigantic stadium-sized rooms. But the majority of players, 4K is really great, and now it really is. It's about better pixels, and making the pixels count that we have and make them really look really great. And there's lots of work to be done there. I would love to see improvements on materials, just being able to simulate more complex materials. I would love to see more work on animation, on the animation front, and do some really cool stuff where we have code running, maybe AI code that can give a more nuanced player experience for the player, where every experience becomes more personal. An experience on that, and work on those type of things. There are lots of things to work on. There's so much work and not enough time. Let's put it that way.
Yeah, for sure. And that actually, one of the things you touched on reminded me of something else I wanted to talk a little, hear your thoughts on as well, as the cutscene stuff, because
Yeah.
it is obviously a more story focused game, and I quite like the cutscenes because they feel, so they're cool to watch, but it's like the types of things the cutscenes do in real time, I feel, are often offloaded to pre-renders, right? You're doing a constant scene switches, so you're like, you're gonna show this location, then this location, then characters here, characters there. There's a lot of complex effects work, things that happen that are at a large enough scale where, again, you normally think, oh man, a lot of games traditionally would just switch to pre-rendered there.
Right.
Even stuff like the logo of the game, unlike the last games which use videos, this one, when it actually reveals Doom the Dark Ages, it's a real-time element. Not that it's super complex to render,
Right.
but like putting in graphics and text and stuff as well. All of this stuff takes
Yeah.
extra time and work, and it shows an attention to detail that I think is really cool. So like, what was it like for you guys, like working up to this level, and like what was the process like, I guess, for building these sequences?
Well, we have. I mean, Darren and the team, our tools team, really made a great new tool called it's basically a cinematic tool that we have that allows us to. It's called Scene Director. And it allows us to build the scenes out. Obviously, the animation team did a wonderful job in our DCC tool pipeline that our DCC tool team did to make sure that everything that was done in Maya can really get really easily transferred into the pipeline and get in there. So that flow from DCC to engine was improved vastly. We use, when Colin came aboard, our cinematic supervisor, he did a fantastic job in organizing and making sure that those concepts that they've done in film are brought over to make these type of flows really more seamless, and brought some really great knowledge there to help us improve our pipeline there. We use ShotGrid, for example, in our tooling to preview things. We now have Lighthouse is an automation system that we use for regression testing, and just like things like reviewing all the cutscenes on all the platforms and kicking out reels of those every second, and then they get put into ShotGrid. There are lots of cool new ways of doing that. When it comes to the real-time stuff, obviously all the load times are vastly helping us to do these camera cuts, because we are jumping from sections of levels from sector to sector. As you can imagine, all these assets are not loaded in memory, so the loading had to be extremely fast. And some of those things we can predict because we know in the cutscenes we know which cut we go to, so we can optimize the loading frequency there. But some things like the GI, which is temporally accumulated, whenever you go from one frame to the next, we had to do a lot of work to make sure that the accumulation and the temporal accumulation of the GI buffers, in the ray tracing, that takes time to accumulate and get the ambient values to be properly calculated. And there's some trickery going there, but it took a lot of work to get that working, but we got it to work, and so it's seamless. So as we are going from like one shot of a different GI solution, and it then has to go to this new scene, and the GI has to accumulate, there's a lot of work that was done. That's still all happening in real time. And the cool thing with that is you can actually, if you were to actually go into development, you can actually go into the cutscene and somebody could move a light around and it would just work,
Oh man, that's so cool.
The atmospherics, for example, Ishan worked really much on the atmospherics, and they're all ray traced, light scattered, all GPU ray traced atmospherics now. There's a really great scene that you probably saw in some of our trailers, where you see the Slayer being blasted from the mothership down
Yes,
into
and
the earth, and you
the
see the
clouds.
clouds emerging. That's all real time. That's not baked.
That's
That's
not an
all real time
animation. That's
atmospherics.
just
Yes.
that's freaking awesome.
And we have a lot of scenes like that. A lot of those things that you see that's all real time, and every time that's doing it properly. So the atmospherics did a great overhaul. The multicolor integration we're doing on some of the atmospherics, etc. It's really great.
Yeah, I also noticed that there's no issues with physics stuff. So a lot of times on camera cuts, physics sort of reset or like they're like interrupted by
Yeah.
that cut, and you see like hair stuff or something just like jump and act weird for
Yeah.
like a frame or two. And I guess like Indiana Jones, this seems to have a strand hair system
Oh
in
yes.
play. So you got like when you see this up close, you get those really super clean strands instead of like the typical like flat card system that what we often saw. That looks really good.
Yeah, the hair strands was something that actually came in fairly late in the project, and
Oh, nice.
we did that in collaboration with Machine Games. So that was a collaborative effort. So kudos and we worked really closely with our peers in Machine Games on that topic. And then they shipped Indiana Jones, and then we were able to take some of the stuff that they implemented, and then we took it. You took the baton and took it a little bit further. But that work there was we had to do that some of that work first in Indiana Jones, and that was Indiana Jones running on the flavor of a Tech 7. And then we were able to take some of those enhancements that we were working on Tech 8 and the X7 and kind of bring them forward to the Dark Ages. The cape, for example, that's all cloth. That's all.
Oh,
That's
right.
cloth and that's cloth and the hair strands working together in symbiosis with the physics. So it's fully simulated. So as you're in the dragon, he's like running with this
Yeah, yeah.
his fur on. It's actually strands, right? So
Yeah,
it's
yeah.
and there's some clever culling happening to make sure that the density stays the same depending on the shot. So as they get closer, you get more density. As you go further, it's slightly density, but the look stays the same and homogeneous. So you don't want to see that shift. And there's quite a bit of work that was done there. The lighting was took quite a bit of time to make that work with the GI and the dynamic lighting and the atmospherics, and make sure that it worked properly with collision on the surfaces,
Yeah,
right?
of
Because
course.
yeah, it worked out really great and looks fantastic. I think there's much more work to be done, and there's some new hardware coming out where NVIDIA, for example, has line swept spheres coming out on the Blackwell cards, and we might play with that at some point.
Very cool. And actually, you should also talk a little bit more about those atmospherics, actually,
Yeah.
because you're right. I forgot to mention that, but that's one of the biggest new things I saw. Is there's like volumetric effects and atmospheric effects
Yeah.
like, all over the place. Obviously, since it's like a darker sort of setting, it relies heavily on this sort of stuff, right? Because you don't have like large, like futuristic fortresses with huge electric light
Yeah.
panels everywhere. So like instead you have a lot of these crevices filled with like sort of fog and mist and smoke
Yeah.
all nestled into the corridors. You've got that freaking just awesome rain effect during the first stage,
Yeah.
where it's just like pounding you down with
Yeah.
rain. In addition to all of that, plus that smoke effect or the clouds moving effect during the intro cutscene, where you're like, I actually did think that was a baked effect. I
That
didn't
wasn't,
think
no.
that it was like a real time thing, but no, that's really cool.
Yeah.
So like, let's hear about it.
Yeah, I mean, you mentioned a lot of different systems there. It's not just the atmospherics, because we have
Sure.
obviously the clouds and some of the stuff you just detailed was the atmospherics. That's all ray traced on the GPU. And we made a bunch of enhancements on our GPU particle system. Ian did a really fantastic job on refactoring the GPU particle system, added a bunch of new ways of doing noise, blue noise, gray noise, etc. to in how we do random numbers, because random numbers are extremely important, and noises is extremely important for
Right.
these type of effects. He spent quite a bit of him and Mel and various others worked really hard on making that run extremely fast and providing more tooling and make it much easier for Todd and the team, like Derek and Sky and Caroline, to be able to create the content there. And that's why the effects look so great. Like the weapon effects look amazing this time around. And
Yeah, they do.
and we worked really hard with Tiago and William worked really hard on making the emissives, the lighting to be
Yes.
very uniform. So we have a new histogram, dynamic histogram that makes sure that the emissives as you go from scene to scene is normalized, and then that the effects and the emissives that are pure emissives, like that come from the particles, work naturally with the rest of the things that are lit through the normal lighting, because particles are pure emissive, they're pure light, right? And sometimes getting the lighting to correspond properly and make them not to be too bright or too dark, or because you create that content once, you want to make sure that that gets balanced out. And we have a new histogram system that makes sure that those things, that the intensity of those values get normalized. So William and Tiago worked on an EV100 system that really allowed the artists to think about how the intensity values need to work across the board. We used the EV100 standard for that, and that took quite some time to get everybody on board. But it also made the lighting more cohesive and more realistic and more sensible, because you can take concepts that you find in photography or in cinematic or cinematography and really apply them directly to the scene, because it now makes sense. You can actually like William, for example, took shots in the world with his camera and then said, I want to color grade the scene like this, and we were able to take those things into DaVinci, come up with the LUTs, and then directly apply those LUTs dynamically into the scene. So there's a lot of work to be done there. When it comes to the effects also, I mean, the light scattering that Tiago and Ishan worked on, the rain effects that Philip worked on and Dominic worked on, that look really amazing. There's some, like Philip, if you notice, like the rain particles on the weapons themselves and how they go down surfaces, and how they flow down. Like Philip did an amazing job on that. That took quite a bit of time to make sure that the specularity was done just right.
It's awesome.
And then Ishan and Dominic working on the rain sequences, on how the puddles, how the rain goes through the scene. So as you're running through the scene and it hits you, that it looks realistic, and then that the ground and the surfaces behave properly. And it's all coming together. There are a lot of big moving pieces to make these things work together, and it's not just one system. It's really, like I said from the beginning, a lot of teams and departments working together, a lot of features working together to get this cohesive look.
That's awesome. It definitely pays off in a big way.
Yeah.
You can cut the atmosphere with a giant blade, I would say, at this point. Actually, the one effect I was thinking of, just as an aside, that I would have loved to have seen, though, is it's like having some sort of effect where, like, let's say you like punch like this, have like the water droplets, give the effect of pooled water being like flung off of your fists. You know what I mean?
Yeah.
Maybe next time.
One other thing that really helped with the look of the game is obviously we unified our tone mapper to ACES 1.3, which is the cinematic tone mapper that is used in film, to make sure that all of our tone mapping is cohesive. In Tech 7, we had a separate SDR tone mapper comparatively to the ACES 1.2 or 1.0 that we used for HDR. And in this game, we obviously used EV100 for normalization of the exposure.
Right.
But for the tone mapping, we used ACES 1.3, and that really standardized things. That allowed us to use DaVinci and tooling like that too, that is used in film, to make sure that we could color grade the scene properly with EXRs, and we could really prototype what the look needed to be in these tooling, and then bring those LUTs in, and then the game would look exactly like that, which is a very powerful tool, not only for the cinematics, but also for lighting the scenes that we have and the different environments that we have.
Cool. Did you do anything with Alembic animation this time? I remember you did a lot of that in Doom Eternal.
Alembics are used quite a bit.
Sweet. What sort of, where do you deploy this?
Some of the destruction, obviously. Some of the large states of destruction that you see. Some of the key moments where, you cannot animate some of those things. I can't think of, I'm drawing a blank here exactly where he's, some of the crowd elements that we had, where in some of the cinematics, use those things. When you see large scale destruction, that is really, really intricate looking, it could be streamed, but there are also ambient things, like just things jiggling in the world, that use Alembic.
Right. Oh, and I didn't even mention the water, which was a nice touch, because this is something. So Machine Games was always good about doing these like geometric rippled water effects, and then Doom Eternal, didn't really go for that too much. I mean, it had a
Yeah.
little bit, but then as soon as you find your first body of water in Dark Ages, it's like, oh yeah, you're sloshing around in there,
Yeah.
enemies sloshing around in there. Doing combat in the water looks pretty sweet. So,
Yeah, we
is
wanted
this
to.
did you guys work with Machine Games, or is this like a homegrown new water system?
Oh no, Dominic and Philip worked on that.
Oh, sweet.
They made the impact work properly. They made the simulation. Ishan worked on that too. We just took what we had from Eternal and just progressed on that and made sure that we could actually manipulate it, and then that the ripples as you're traversing through as you're wading through water, or AI wades through the water, that there are ripples. Like Dominic and Philip worked on that really well. So, and Ishan as well. So that was a concerted effort. We wanted to make sure that the world felt lived in, and that what you do in the world has an impact, and water is the same. Same with the light scattering you see as you're swimming around and things like that.
Yeah. I love that stuff.
And the caustics effects and all those things. Yeah.
Another thing, of course, it's Doom. Well, it's the new flavor of Doom, which is extremely violent Doom. So there's lots of gore. But I did notice actually that the glory kill system's kind of been replaced and changed, and it does function differently, but which is cool. It's a different touch. But that doesn't mean there's not a ton of freaking gore in this game. I think it's like version 3.0 of the gore system now. It's pretty effective. It's pretty gnarly. Why don't you talk about it?
Yeah, I mean, there are still glory kills in there. It's just in the game, I think there's 3.0 has glory kills plus more, right?
Right. Yes.
It's just we just added more capabilities, and we enabled the capabilities that the game required to make the stand and fight experience that we wanted to have feel the flow of melee combat with weaponry, etc. We wanted to make that feel really immersive and impactful, and so those sequences still exist. They're just done in a slightly different way.
I would say, if I could interject there, it's like it doesn't wrestle control away from the player as much.
Right.
It feels like you stay in control as the animation executes, which I thought was a nice touch.
Right, and that's intentional because, again, the whole notion of the game is stand and fight.
Right.
So, and we wanted to make that feedback that we have, that you get, that you feel like in control of the situation, and that whenever you give control to the player and they feel like what I'm doing is directly seen in the world, that has the most impact many times. So the weapons,
yep,
I do something, there's an effect, and being locked into something sometimes can detract from that. So we wanted to have a balance of that, of doing it at the right moments when it's necessary,
right,
but also make the player feel as most in control as we can. And because we have these great combos that we do now, if you notice, like with the flail and the mace and the shield and the weapons, there's a flow to it. It's almost like a gung fu that you see in certain movies, right? And that parry system with the shield and that dance that we have, that combat dance, we wanted to make sure that felt really impactful and fluid. So we made some tweaks. One of the major improvements is Todd, one of our technical artists that works on the effects side, wrote some great tooling on the Houdini side to generate a lot of gore bits automatically. And then our artists can take that work and because it's quite intensive to create all the bits for all the characters, right? Especially with all the flavors of characters we have. So we used Houdini and his tooling to create a bunch of that stuff. So Todd did a wonderful job on that. And then a lot of our artists, like our character art team, did a great job of making the gore look really gory and bloody and so on. Ian, when he was working on the liquid effects for the blood and stuff, that had made a major impact. And of course, all the physics work that Peter and the Destruction team and did, and Tad, our technical group that works on the design side, putting those pieces together to make that the gore system really shine and make the gameplay really shine. So I would say it's a progression, it's an enhancement, and there's some meaningful changes there that were made to make the experience that we wanted to simulate just work well. So it's Jean worked really great on how making sure the visuals worked really well too, and how the pieces on the rendering side, because they're quite costly, because if you imagine having a character usually is made out of one hull, but now you have to build the character out of a bunch of pieces. So there was some quite a bit of work done as Jean did to make sure that the Gore system flowed, the data for that worked really well with our multi-composite materials, for example, that we have. We haven't even talked about the multi-composite materials. We probably should do that.
Yeah.
And make sure that as we're building the content, that all that data that's required for the lighting from the main mesh also works properly with the Gore pieces. And as we go through the LODs, for example, that all works well too. That's quite a bit of work to make that work.
Okay, so there's a lot that we can branch off to from there. So the first stop I actually want to make is the fluid system. So like fluid simulation and such that you mentioned.
Oh yeah, the wind fluid sim. So one of the things that is, since the world is larger and you're running through these open spaces and you have these large comment spaces, we wanted to make the world feel more lived in. So we have Philip implemented the GPU fluid sim, which does all of our wind simulation. That's all done dynamically on the GPU, and it runs all the time. And all the wind that you see gets that information interjected. So the banners you see floating in the wind, and like for example, the wind can have an impact on even the physics. So if something has mass but there's a big wind blowing, it might flow in a certain direction and so on. And then or trees blowing in the wind, and if the wind direction changes, that would go naturally. So that was it's a nuanced thing that you may not notice right away because it just looks correct, right? But the point was that everything goes to the same simulation, and so all the pieces that might behave slightly different, like the vegetation and the physics, etc., these are different systems, all work with the same type of inputs when it comes to impulses, all coming from this fluid simulation that's done on the GPU.
Oh man, that's radical. Yeah, I definitely I definitely noticed that the world does feel very alive as a result of this. So it's definitely a nice touch.
We call that secondary animation.
Yeah, secondary animation. Exactly.
Right. So we wanted to add a bunch more secondary animation into the world to make the as you're running through the world, it's like you actually feel like you're there. So like there's a lot of atmospherics, there's a lot of wind, there's things behave properly as you interact with them. The characters, as they're going through the world and wading through the water separates. All those things go together to make the experience feel like you're actually there, taking on the demons, right?
Yeah, absolutely. What was that next thing that you mentioned?
Composite materials.
Yes, composite materials. Let's talk about that.
Multi-composite materials. That's some of the major improvements in the Tech 8. Excellent. You started off. So when it comes to like when you create surfaces and like all things that you see that are being rendered have meshes, right? And we call them surfaces. And so many things like when you model them, they have many surfaces, so many meshes in them. And then you obviously have to texture them, and they get a material applied to them. Well, traditionally, you usually have a single material per surface. And in Tech 8, we actually have a multi-composite material where each surface, each triangle, each pixel may be made of 8 different materials, up to 8 different materials, all being blended together in real time. And up to 8, right? And there are different ways of where you can blend them in. So the reason we do that is because we have a fixed amount of memory. And by doing so, we can get much more complex visuals because we can take tile textures and we can get a bunch of detail combined on top of each other rather than making a bunch of large textures with the details baked in. So there's these tooling such as Substance Designer and Substance Painter that are in the DCC world. Well, materials you generally are built that way. You have all these different layers, or in Photoshop, if you were to use Photoshop, make all these layers. And we're basically doing that in real time with real materials. And the material for us is really a full stack. It means albedo, specular,
right,
normal,
for each material.
For each material, and then you can have up to 8 stacks. So you can imagine how many different things you can blend together. And then the artists have the capability having multiple UV layers to control all this. So each surface can have multiple UV layers, and then they can control how those blend together. And then there's this concept of height maps that they can push and pull various things in there. And so you can do things like, I can have a sheen of dirt on top of something that may not exist in the original layer, but it's just there. So you can then also swap them out. Like One time it's dirt, sometimes it's grass, sometimes it's water, sometimes it's something else. So you can do different effects with that. You can get way more detail and reduce your texture footprint because your natural textures don't have to be so large. It also allows you to do the concept of fading features in and out that may not be relevant based on view distances. So the literally like high detailed stuff. Like back in the day, some of these things were called detailed textures. We're now doing that with full material stacks though. So rather than having like a detailed texture that gives you like some scratches or something, and it's just on a detailed texture, we now do that with full materials. And all those things are blended together. And the cool thing with us, we used to use this on characters and on Tech 7 to some degree, but now we expanded that to every single piece of mesh or geometry that you see can have these multi-composite materials, and that allows us to reuse textures, allows us to have a homogeneous look when it comes to, we can have a new texture department that's run by Nicholas Clark, that where the texture team has full control and make sure that the PBR setup of all those textures is done controlled. And the team can work really closely with the character team and the lighting team to make sure everything looks cohesive. And then you can also do cool things where you say, you can steer things with the multi-composite materials. That has a new concept of being able to steer, okay, well, in this case, I want to use really high MIPS, and I have one texture that's 4K, and I use all the way up to MIP 0, but in another case, I may only want to use that same texture, but I only need to go up to MIP 2 or MIP 3, which is a smaller footprint, so when it gets to that point, I don't need to load the whole texture in. And allows us to stream things more cohesively, so Oliver, when he does his streaming, can be really informed what MIPS to load in at what times, optimize them as we run through the level. And it gives us a lot of control to give way more detail without increasing the footprint massively. It's extremely powerful. It took some time for the artists to learn how to use this, and I think there's still quite a way we can make that more powerful. But Jean did a wonderful job of making multi-composite work with Thiago and the rest of the team. And I think it's an idea that we started off, like one of the early prototypes I implemented was in Tech 6 when we had the customizations for a multiplayer. That was the first prototype of composite materials that I did there, and then we took that forward in the Tech 7, and then now in the Tech 8 it came to its natural conclusion where we now have full stacks of materials that can be replaced at runtime, they can be adjusted, they can be dynamically so you can do material swaps and runtime for between layers, and then we can also turn them on and off for detail. And that in the combination of how the content's created in Substance Painter, in addition to doing it all in real time, allows us to really control the content where we can have super high fidelity in cinematics, but then dynamically reduce the cost of it when those things are seen in the game without having to duplicate work, which is really a great way of doing it. And
that's awesome.
So when you look at the weapons, for example, in the model viewer in the game, you can really see that really great detail we have, or the characters. And some of that detail may go away as you're playing the game if they're really far away, but it's still there. It's just not being acted because the multi-composite materials allows you to have that fine control, combined with the contribution culling, combined with the streaming capabilities we have, combined with the LOD systems we have, etc. All those kind of systems work together to have the best quality pixel depending on what you're looking at and what the purpose is, and not duplicating.
Right.
And all done dynamically, which is the key here.
It seems like it's a smart way as well, like you said, to sort of reduce overall memory footprint, which is perhaps very useful for like lower memory environments or like GPUs with less VRAM or something, right?
Oh yeah, our image streamer we can have the amount of quality we can have is probably increased by 8-fold just because we can have smaller textures because the textures are used more nuanced and more meaningful.
Exactly. That's good. That's really good. What else is there that we should bring up? Anything else come to mind?
We can talk about the cloth.
Yes, the cloth stuff.
We also... go ahead.
I was gonna say, yeah, obviously between we already talked about the fur cape, but there's a lot of cloth in this game.
Yeah,
Flags. Characters wearing stuff. Like there's just lots of situations where you get that smooth flowing cloth
yeah.
simulation that does sort of react to both the wind sim and also like things happening around you. So that's not something I really recall from Eternal at all, or maybe slightly. I don't. What's up with the cloth?
So cloth is brand new for Tech 8.
So it is all brand new. Cool.
Yeah. We used Havoc cloth for this, but there's quite a bit of work that Bogdan and Mel and Peter did and Stefan did on the cloth simulation from a tooling side with the DCC tooling team, and on the content creation side and the rigging team, for example, because we have the concept of like being able to control the cloth via animation for some cases, but then you need to also go from animation back to simulation and make that seem seamless.
Right.
So you can have really cool intrinsic movement that's done through animation if desired, but not all. And you can also do dynamic and blend in the simulation on top of it if you want to have it being affected. So you can transition from maybe being fully simulated to partially simulated to fully animated. There's also how many nodes and particles the cloth is simulated with is very important, and making sure that the weighting is correct. And then, of course, doing the strands hair on top of that to make the cape work. And that all working as you're riding on a Slayer, flying at Mach 10 through this gigantic world and making that look great. All those things are really fun to work on, and Mel and Bogdan and the character team and the riggers did a wonderful job making that work. And I remember when Wayland worked quite a bit on the cloth for the Slayer cape, and it took quite a bit of iterations, but we just got it right, and it looks amazing in the game.
Yeah, it does. It looks freaking awesome. Absolutely. Yeah, there's just so much dynamism on screen at any one point, and it really works. It pays off in a big way.
Yeah.
And yeah, okay. So when we last talked about Eternal, by the way, one of the things I asked you back then was if you had an estimate on the sort of triangle count in any one like stage, right? And I think you mentioned the Super Gore nest maybe as being the most dense stage in Eternal, maybe.
Yeah.
I'm wondering if off the top of your head, if you have any rough numbers on just like how complex a stage has gotten. Like, what are we talking here?
So Gore Nest was the most complex, right, we've ever done in the
right.
Tech 7.
It was nuts.
Now imagine all of Gore Nest in one sector, which is only a tenth of a level.
Okay, so like
that's the density we're talking about.
Like 10 times that then.
It's about 5 in some cases. In average is around 5 to 6 times. In some cases, up to 10 times more detail. When it comes to not only just polygons, but just geometric, compositionally, items in the world. Like,
individual items are all more detailed now, right?
All the things that we used to have, that we used to load for the entire map, now can be in a sector. Right. And at one point, 1 or 2 sectors are loaded. In some cases, only 1 sector is loaded, which means all the content you would traditionally have in one level could be just in that sector you're currently in.
Just one sector.
And one sector. And some maps are 4, 5, 6, 7, 10 sectors. So depending how big it is or what space you're looking at or views you're looking at, the density flows back. And now our culling system is all done on the GPUs, does a fine job. And the optimization to get, and since we're doing everything on the GPU, one of the optimization techniques we use to make that all work is we used this concept of visibility buffers. And are you familiar with how visibility buffers work?
Yes, indeed.
So Jean-Philippe, Dominic, Thiago, and many of us, we worked on visibility buffers, and that's one of the things that we do to make that culling work, but also optimizing the scene graph to make sure that we really light the scene as sufficiently on a per pixel level, and also make sure that we reduce the opaque cost, because in some cases we can bring the cost down tremendously, and the trick is really just how that works, right? And it's the pre-Z writes out depth, not only depth like traditionally, but it also writes out triangle and surface ID into a buffer. And then there's a tile classification pass, which generates work items for further deferred passes. And that work is generated in such a way that the surface of a similar materials can be grouped together. And then what happens there is for surfaces of compatible shaders, meaning that they're classified as, these can be used to defer texturing path. The whole standard opaque pass that we usually used to do is completely skipped. We don't even do that anymore.
Oh, really?
Yeah, so all of that's done. The visibility buffer basically allows us to optimize major sections. So instead, what happens is we have a deferred texturing compute shader that fetches all the triangle data from the visibility buffer and the geometry data buffers. And all that shader performs material evaluation and blending, and then outputs G buffers. And then later, we run a deferred lighting pass, which reads from the visibility and G buffers to perform all lighting computations. So the main benefits of this approach are that there's a single geometry pass, standard bottlenecks that you have of rasterization performance, or things like parameter cache or shared register counts like VGPRs between the vertex shader and pixel shader waves are really not relevant anymore during the opaque pass. It helps with better quad utilizations. As you know, everything is rendered in 2x2 quads. Many times you have under shading where helper lanes are used, where like only one pixel of the quad is used. And so in the standard pixel shader, everything's happening quad. So on triangle edges, for example, we can have quads of a single useful pixel, and the 3 helper lanes whose sole purpose is to compute derivatives. Sometimes it's completely wasted. So all that work is wasted. But for texturing lighting, all threads perform actual useful work. We don't use performance because 2 or 3 helper lanes are doing useless work basically in that cases. So by splitting the material evaluation and lighting, we can run much simpler shaders. They can now have different occupancy requirements, smaller code size, and ideally help the compiler generate better code just by virtue of being simpler.
Very, very cool. We could probably go on, but I feel like I've got enough material here to last quite a while. So thanks for joining me for this one, Billy.
All right. Thank you. Appreciate you taking the time.
And thank you to everyone for watching. We'll see you next time.